Today, we're going to go on a journey. It's a really cool one that turns this, jumble of raw data into clear, actionable knowledge. So think of this as your map, your cheat sheet for understanding the world through numbers. Let's dive in.
Have you ever seen a headline or some study and just wondered, how on earth did they figure that out, right? How does a spreadsheet full of numbers become a confident conclusion like X causes Y? Well, it's not magic. It's actually a structured process. And today, we're going to walk through the map for that transformation step by step. So our journey kicks off with phase 1. And, like any great adventure, it all starts with gathering your supplies. For us, those supplies are data. And I can't stress this enough. This first step is absolutely critical because the quality of what we collect right now, well, it determines the success of the entire journey.
Okay, so in a perfect world, we would study everyone we're interested in, the entire population. But let's be real, that's rarely possible. It's usually too big, too expensive. So what we do is we study a small, manageable group called a sample. And the whole goal, to use what we learn from this small sample to understand the bigger picture, the whole population. So how do we actually choose our sample? Well, there are two main ways to go about it. On one side, you've got probability sampling. This is really the gold standard for big studies because it's random, and that helps avoid researcher bias. It's what lets us do powerful statistical analysis that can apply to everyone. Then, on the other side, you have non-probability sampling. This is more focused, often used for really in-depth qualitative work, but we just have to be really aware of its potential for bias.
All right, our supplies are gathered, we've got our data, now we can move on to phase 2. And with our sample data in hand, this is where the real fun begins. We can start making educated guesses, what statisticians call inferences, about the entire population that we couldn't directly measure.
And there are basically two ways to make these guesses. A point estimate is our single best guess. It's like throwing one single dart at a target, hoping you hit the bullseye. But an interval estimate is often way more useful. Think of this like casting a wide net and saying, hey, I'm 95% confident the true answer is caught somewhere inside this net. It gives you a range of plausible values.
But what if we already have a theory that we want to test? That's where something called hypothesis testing comes in. And a fantastic way to think about this is like a courtroom trial, but for an idea. We have a claim, and our data, well, that serves as the evidence we use to reach a verdict.
Now, at the very heart of this trial is the null hypothesis. And this quote just says it all. Think of it as innocent until proven guilty. It's the default state, the status quo. It's the assumption that, nothing interesting is going on. Our job as the data detectives is to see if our data provides strong enough evidence to reject that initial assumption. But, just like in a real trial, verdicts can be wrong. A type 1 error is basically convicting the innocent. We see an effect in our data that isn't really there. A type 2 error is the opposite, letting the guilty go free. We miss an effect that actually exists. And there's always this tricky trade-off between trying to avoid these two risks.
So we've made our educated guesses. Now it's time for phase 3, connecting the dots. This is where we move beyond just describing single variables and start to uncover the hidden relationships between them. This is where it gets really powerful.
Our main tool here is something called simple linear regression. Now, don't let the equation intimidate you at all. We're essentially just asking a simple question. How does X explain Y? That little beta or beta symbol, that's the magic number. It tells us the slope of the line. So for every 1 unit change in X, how much do we expect Y to change? It's really all about finding the single straight line that best fits all the dots in our data. But for this tool to give us trustworthy results, we have to follow some golden rules. Essentially, the errors, and that's just the part of the data our model can't explain, they need to be completely random, with no weird underlying patterns. If these rules hold up, great, we can trust our findings. If they don't, our model might be seeing things that aren't really there. So what happens when those rules break? We run into some problems. Heteroscedasticity is a mouthful, but it just means our model gets less predictable at different levels, which makes our conclusions a bit shaky. Multicollinearity means our explanatory variables are all tangled up, so we can't tell which one is actually causing the effect. And autocorrelation means our errors have a hidden pattern, which is a big hint that we've missed a key piece of the puzzle. All of this leads us to our final phase,
tackling real-world messiness. Because let's face it, the real world is rarely as clean and simple as our models assume it is. So we need tools that can handle all that complexity. For example, our regression model is great for predicting numbers, right? Like price or temperature. But what about predicting a choice? A yes or a no? Will this person buy the product? A linear model can't really handle that. For those kinds of questions, we need different tools, like discrete choice models, which are built specifically to model the probability of making a choice. So let's zoom out and take a look at our completed map, our data journey cheat sheet. And here it is, the complete flow. Phase 1, get the data. Phase 2, make educated guesses and test our ideas. Phase 3, find the relationships between variables. And finally, Phase 4, adapt our tools for the messiness of the real world. It's a logical, powerful, and totally repeatable process for turning raw data into real insight.
So there you have it, a map for turning data into knowledge. The key takeaway here is that there is a proven process for answering questions with data, which really leads to one final question for you. Now that you have the map, what will you investigate?